Hi guys, today we're going to talk about sigma bonds and pi bonds. So we're going to start with sigma bonds. Sigma bonds are when you have electron orbitals overlapping along a linear axis. And sigma and pi are both Greek letters. The symbol for sigma looks like this. So it's kind of like an O with a little tail added to it. Let me do it in another color, kind of like that. Pi, you're probably all familiar with it. It looks like this. So with sigma bonds, all single bonds are sigma bonds. And basically the first bond between any two atoms, so the first connection between any two atoms is a sigma bond as well. And so again, we have an overlap along a linear axis. So our choices here for sigma bonds is you can have an overlap of two s orbitals, or two p orbitals, or an s and a p orbital. So if you remember, s orbitals look like a sphere, p orbitals look like dumbbells. So if I have two s orbitals, so imagine two spheres overlapping like this, this overlap is going to be our sigma bond. If you have two p orbitals, so you have there's the first dumbbell, here's the second dumbbell, and so this overlap would be our sigma bond. Or if you have an S and a P, so there's your sphere, there's your dumbbell, this overlap would be your sigma bond. Pi bonds are the second or third connection between two atoms, and so those only occur with p orbitals, no s orbitals here, and it is a parallel overlap as opposed to a linear overlap. So remember, p orbitals look like dumbbells, and so we have p orbitals that are in the x plane, the y plane, and the z plane. So let's look at these first. And so here you have a parallel overlap right there. That would be a pi bond. Or let's say you're in the z plane like this, then there's a parallel overlap here. Or in the x plane, so there's the overlap. They're kind of like parallel to each other, and that's where your overlap is. And so that would be a pi bond, and this only occurs in double and triple bonds. So if you have a double bond, the first one is going to be a sigma, and then the second one is going to be a pi. If you have a triple bond, the first one is going to be a sigma, and then the second and the triple, and the third one will be pi. So the first connection between any two atoms is always a sigma. The second or third connection will be a pi. So all single bonds are going to be just sigmas. A double bond, you have a sigma and a pi. A triple bond, you have a sigma and two pi's. And so that's what it says right here. Now, this next page is kind of a visual to show you what we mean by hybridization. When it comes to hybridization, we've kind of talked about it being mixing of orbitals. We don't really know what that really means. So I'm going to draw some diagrams here. You are not responsible for being able to draw these diagrams. You do need to be able to, looking at a diagram that's already written for you or drawn for you, you should be able to like spot a sigma bond or a pi bond, but you do not need to be able to draw these. So let's start with C2H6. So C2H6 looks like this. You have two carbons that are singly bonded, and then each of those carbons have three hydrogens around them. And if we look at just carbon by itself, just one carbon by itself, remember that carbon has 4 valence electrons, right? And so the first 2 go into the s orbital, which looks like a sphere, right? The probability density graph of it is a sphere. And then these are p bonds, or sorry, p orbitals. And so those electrons are in the p orbitals, which, again, remember the p orbitals, when you graph them, look like dumbbells. So we know that in order to bond the carbon to 4 different things, one of these electrons needs to move here, right? Because this carbon needs to have an electron in each of those in order to bond to 4 different things. So, we'd still expect that, 3 of those would look like dumbbells and one of them would look like a sphere. But in reality, what we found out is that all of them kind of look like they've mixed. So let's draw this first. So this is just the carbon that is not bonded. So we have 2 electrons in the s orbital, right, to show this, and 2 electrons in 2 different p orbitals. Now, in reality, and then this p orbital is empty. Now, in reality, what we saw is that we did not see any spheres, we did not see any dumbbells. It looked like all of these have mixed together. So this s orbital and these 3 p orbitals all mix together. And so when they mix together, we call that a hybrid. Hybrid means mix. And that mix is 1 part s and 3 parts p. And so we call it sp3 because it's made up of 4 orbitals that have mixed. 1 of those is an s and 3 of those are p's, so sp3. So these 4 orbitals that mix together turn out to look like this, turn out to look like 4 sp3 mixed orbitals. And so those electrons are now 1 electron in each of those 4 sp3 orbitals. And again, these don't look like a sphere or a dumbbell. They kind of look like a hybrid. They look like this in between. So now let's look at this in terms of a diagram of what's happening. So I'm going to go ahead and draw my carbons here. So there's a carbon, there's my second carbon. And those carbons, each of them, their orbitals have mixed, and now I have, again, those 4 orbitals mixing together to give me 4 sp3 orbitals. And the sp3 orbitals kind of look like this, and so I'm going to go ahead and show those in blue. And so there's an sp3, there's another sp3, here's a third one, and here's a 4th one for this carbon. And I'm going to do the same thing for here. This carbon has 1 sp3 here, 1 here, 1 here, and 1 here. So all of these are sp3s. I'm going to try to write sp3 in them here. Okay, so we start seeing an overlap right here. There's an overlap that is this bond that we see right here. Okay, I'm going to go ahead and erase these other bonds so you can see what they look like eventually. But this bond that's in between the 2 carbons, that's my sigma overlap that's right here. And it's sigma because it's a linear overlap. Okay, now let's look at the hydrogens. The hydrogens, I'm going to do those in red here. So I have 6 hydrogens. And the hydrogens have just the 1 electron in the s orbital. And so the s orbital, remember, looks like a sphere. So there's 1, there's 1, there's 1, here's another, and here's the last one. And see right here, there's a linear overlap between each of those hydrogens and the carbons that they're bonded to. And it's a linear overlap, so these are also sigma bonds. And so that's these bonds that are right here. These 6 bonds are a linear overlap between the sp3 orbital of the carbon and the s orbital of the hydrogen. And so that's kind of a picture to show you these sigma bonds that are overlapping. You can see that there are 7 sigma bonds in this molecule. There's one right here between the carbons, and then there are 6 between the carbon and the hydrogen. So we have 7 sigma bonds. Now, if we did not draw this with the overlap, you don't actually need to look at this diagram. If you just look at this, any single bonds are always going to be sigma bonds. Any first connection between any 2 atoms is always going to be a sigma bond. So any of those single bonds are sigma bonds, and there's 7 of them, so that's 7 sigma bonds. Okay, now let's look at a double bond now. And this is where really hybridization, I think, starts to make sense. So let's look at C2H4. So I'm going to go ahead and draw C2H4. So C2H4 looks like, oops, didn't mean to do yellow, there we go. Double bond between the carbons, and then each of those carbons is bonded to 2 hydrogens. Now, we know from just our past experiences that this carbon, or this carbon, is an sp2 hybrid, right? Now, to be honest with you, as a student, this drove me crazy. I did not understand this at all. So the way that we memorized how to do it, which really was just memorization, we didn't really understand what it means, and that's what bothered me, is we said, oh, around the central atom, there are 3 areas of electrons. And so if there are 3 areas of electrons, that means 3 orbitals mixed. One of them is an S, 2 of them are P's, so it's an sp2 hybrid, right? That's how we've always done it. But that makes no sense because, well, you know, you have 8 electrons. Like, this double bond here, that's not one orbital, right? Remember, an orbital only takes 2 electrons, and there's 4 electrons there. So again, as a student, that just really, really bothered me until I actually started studying these diagrams, understanding what they mean. So let's look at just a carbon by itself that's not bonded again. So remember, we have these 2 electrons in the s orbital, and then we have 2 electrons that are in p orbitals. So when we say there are 3 areas of electrons here, which means that we have 3 orbitals mixing, in reality, these are the 3 orbitals that mixed. So one s orbital mixed together with 2 p orbitals to form 3 orbitals that are 1 part s and 2 parts p. And so now those electrons are in these 3 sp2 orbitals. And so again, these are the 3 orbitals that mix together. So what about this orbital? This orbital, let me actually draw this electron in a different color so you can see it a little bit better. Let's make that orange, for example. This electron is still a pure p orbital. It did not mix. We don't have sp3 orbitals here. We only have sp2s. So we only have 1 s and 2 p's mixing together. Those are the ones that mixed and turned into these. This one remains as a pure p. So let's look at a diagram to kind of help us understand what that means. So I have my 2 carbons here. Now these carbons each have 3 orbitals that are sp2. And remember, an sp2 orbital kind of looks similar to an sp3. It's kind of in between like an s and a p, right? So let's draw that. So we have 3 of those. There's 1. Here's 1. And here's a third one. So that's for this carbon. Let's do the same thing for this carbon. So here's 1. Here's 1. And here's 1. And I'm going to go ahead and label those as sp2 orbitals. Each of those is an sp2 orbital. So this carbon has 3 sp2 orbitals, those 3 orbitals, and this carbon has also 3 sp2 orbitals. Okay, and you can see the first overlap, which is right here. That is my sigma bond that's in between my carbons. So that is this bond right here. Okay, great. Now let's look at the hydrogens. So I'm going to go ahead and draw my hydrogens. I have 4 hydrogens here. I'm going to go ahead and make it a little thicker. And so each of those hydrogens have an S, just an electron and an S. Right, S looks like a sphere. So there's my overlap, linear overlap right there. And those 4 bonds are right here. Okay, so then what about this orange electron here that I have drawn? So remember we said only 3 of the orbitals mixed together to form the sp2s. This one remained as just a pure p, right? Just a p. Well, so each of those carbons has an electron in a p orbital. Remember, p orbitals look like dumbbells, so I'm going to go ahead and draw them here. So there's a p orbital, and here's a p orbital for that carbon, and here you have this parallel overlap. I know it looks like there's 2 of them, but it's really just one. It's this is just one orbital, and there's another orbital. And so those 2 orbitals are overlapping parallelly. That is your double bond that is here. And that is a pi bond, and that is made with 2 electrons that are in pure p orbitals that have not hybridized. They're not sp2s, they are just pure p's. Okay, let's look at another one. Let's look at triple bond now. So we have C2H2. C2H2 looks like this. And from our past experience, we know that that's an sp hybrid, right? Each of those carbons is sp hybridized. What that means is we have 2 areas of electrons, and so that tells us that the 2 orbitals have mixed together, 1 part s, 1 part p, and so we call it sp. But what does that really mean? Well, remember again, there's the unbonded carbon. It has 2 electrons in the s, and then it has 2 electrons in 2 p orbitals. So what we're saying here is that there are 2 areas of electrons, which is telling us 2 orbitals have mixed together. Well, guess which orbitals have mixed together? It is these 2 orbitals right here. Those 2 orbitals have mixed together. Let me make it like that. And those 2 are now 2 mixed orbitals that are 1 part s and 1 part p, and so we call them sp. And so those 2 here are those. I'm going to go ahead and draw these 2 other electrons in different colors, just so that we can see them a little bit better. Let's make one of them maybe orange and one of them green. There we go. So these are my original 4 electrons. In reality, those 2 orbitals mixed together to form the 2 sp orbitals. These 2 are still pure p orbitals. They have not hybridized. They have not mixed together. So let's draw what that looks like in terms of the structure. So we have 2 carbons. Each of those carbons have 2 sp orbitals. Remember, sp orbitals, any mixed orbitals of s and p kind of look like this, kind of look like a hybrid, a mix between s and a p. So for this carbon, here's the first one. Here's the second one. For this carbon, here's the first one. Here's the second one. And I'm going to go ahead and label those as my sp orbitals. Okay, and you can tell there's my first overlap right here. And so that is my first bond between the 2 carbons. So there's my first carbon, there's my second carbon. This right here is this overlap there. Okay, now let's draw my hydrogens. So I have 2 hydrogens, one here with an S and one here with its lone electron in the S. And this overlap is a linear overlap, that's a sigma. And that's this hydrogen and the single bond hydrogen. Okay, so then what about those? So let's start with the orange. So this orange electron is in a p, pure p. And so I'm going to draw there. That's my p orbital for that carbon. My other carbon also has that p orbital. And so there's an overlap right there. And again, it looks like 2 of them, but it's really just one. It's the linear overlap. That makes my first pi bond, or my second bond that's here between the carbons. So then what about this other electron that's also in a pure p? So remember, p orbitals could be, it's in the x plane, the y plane, or the z plane, right? So we're going to draw this one like that. And you can see there's a parallel overlap right here, and that is my triple bond that's there. And so if I look here, I see 3 sigma bonds, right? This is a linear overlap. There's one. There's a linear overlap. That's one. And there's a linear overlap. That's one. So the red and the blue, these are all sigma bonds. So I have 3 sigma bonds here. And then I have 2 pi bonds. Where are my pi bonds? One of them is the orange with the parallel overlap, and one of them is the green with the other parallel overlap. Let's go back to our C2H4. We didn't really count our sigma and pi's here. So let's count those. So any linear overlap, this one, this one, this one, this one, and this one. So all the blue and red again. So this, this, and this. These are all sigma bonds. So we have 5 sigma bonds here. We only have 1 pi bond, 1 parallel overlap, which is the orange, this here, and that overlaps. So 1 pi bond. So again, I know that this is kind of complicated diagrams. You do not need to be able to draw these. This is just for you to understand, what does hybridization mean? What does sigma and pi mean? You will not be asked to draw these. You do need to be able to, if you look at a diagram, be able to tell, oh, that's a linear overlap, so that would be a sigma. versus that's a parallel overlap, so that would be a pi. That's all you'd have to do. And then looking at a structure like this, being able to count how many sigma or pi bonds that you have. So let's practice the sigma and pi bonds real quick with a couple of these. So let's look at this structure. We want to know how many sigma bonds and how many pi bonds. So remember that the first overlap between any two atoms is a sigma. So there's a sigma, that's 1, 2, 3, 4, 5, 6. So 6 sigma bonds. Okay, how about the pi's? The pi's would be a second or a third overlap. So this would be a pi bond, this would be a pi bond, and this would be a pi bond. So we have 3 pi bonds here. Okay, let's look at the hybridization of atom 1. So this carbon right here, 3 areas of electrons. So that means that 3 orbitals have mixed together. And so 1s, and we'd need 2 p's, so sp2. Hybridization of atom number 2, this carbon has 3 areas of electrons, so 3 orbitals mixed together, 1s and 2 p's. How about number 3, 2 areas of electrons, so 2 orbitals mixed together, an s and a p, so just sp. Let's look at bond angles. Bond angle A. So again, this carbon has 3 areas of electrons, and so that bond angle would be 120 degrees. How about B? So you look at that carbon, 3 areas of electrons, so 120 degrees. So angles in hybridization, you always base that on how many areas of electrons are around your central atom. Don't let the picture fool you. Sometimes they'll draw them with different angles. Don't worry about the picture. You go with the number of areas of electrons. Okay, how about C? So this carbon has 2 areas of electrons, so the bond angle would be 180 degrees. Let's practice this one here. So we want to know how many sigma and how many pi bonds. So let's start with my sigma. So any first connection is a sigma. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. 14 sigma bonds. Let's look at the pi bonds. So the pi bonds would be the second or third connection. So this one would be a pi, this one would be a pi. So it looks like 2 pi bonds. Let's look at the hybridization. Let's look at atom 1, 3 areas of electrons. So that would be sp2. Number 2 here, 3 areas of electrons again, so another sp2. Carbon number 3, 4 areas of electrons, so that would be an sp3. Carbon number 4, 3 areas of electrons, so sp2. And carbon number 5, 4 areas of electrons, so sp3. Let's look at some bond angles. Bond angle A right here. So you look at this carbon, 3 areas of electrons, so the bond angle is 120. That's what you base it on. Let's look at angle B. This carbon has 3 areas of electrons, so need to be 120 apart, so 120 degrees. How about C? Right here. This carbon has 4 areas of electrons, so to stay as far away from each other as possible, it needs to be 109.5 degrees. D, right here. This is a tricky one. What does it look like? It looks like it's almost linear, right? It looks like it's 180, but it's not. If you look at that oxygen, that central atom, 4 areas of electrons. So 4 areas of electrons, what angle would that be? That would be 109.5. I bet on the test this will trick some of you. So don't base it on the picture. We're drawing 3D molecules on 2D paper. So It looks like it is linear, but in reality it's not. It's just like water, right? Water, you can draw it like this, or you can draw it like this, right? That angle, whether it's this one or this one, is really 109.5 or 104.5. It's a little bit smaller. It's not 180. It is not linear, so watch out here. And finally, E, 4 areas of electrons, so again, 109.5 degrees. Bond order. We haven't done bond order in a while. So bond order for atom 1. So remember how to find bond order. You take the number of bonds that are bonded to that central atom, so that carbon. So there's 4 bonds. And you divide it by the number of atoms that it's bonded to. So 4/3 or 1 1/3 is the average. Atom number 5, let's look at this one. This carbon has 4 bonds, and it is bonded to 4 different atoms. So 4 over 4 is 1, so the bond order is 1. And that's it for our notes for this chapter. Have a great rest of your day.